Greetings, everybody. Learning is a hobby here. In this video, I'm going to do my solutions to the exercise set for section 5.2 in Tao's analysis 1. It's a very short section. This video is going to be like 3 minutes long, probably. But, we have to do the problems. So let me bring up my solutions and we'll just go through them here. Okay, so here we go. The first question, 5.21.1, says show that if AN and BN are equivalent sequences of rationals, then AN is a Cauchy sequence if and only if BN is a Cauchy sequence. So here's my proof. Let epsilon be greater than 0, be an arbitrary positive rational number, and let AN and BN be equivalent sequences. Those were the hypotheses. And then without loss of generality, actually, we can just assume that AN is the Cauchy sequence because, there's symmetry here between the equivalence equivalence of the sequences that's symmetric. So then there is capital N greater than or equal to 0, such that the distance between AN and BN is less than or equal to epsilon over 2 for all for all n greater than or equal to capital N and m greater than or equal to 0, such that AJ minus AK less than epsilon for all JK greater than or equal to m, because remember we said was a Cauchy sequence. So let JK be greater than or equal to m plus n, then consider the distance between BJ and BK that's equal to the distance between that's equal to the absolute value of BJ minus AJ plus AJ minus BK, which is less than or equal to the distance between BJ and AJ plus the distance between AJ and BK by the triangle inequality, which is less than or equal to epsilon over 2 plus epsilon over 2, which is, of course, equal to epsilon, so that's less than or equal to epsilon. Therefore, Bn is eventually epsilon steady for every epsilon greater than 0, which means that Bn is also a Cauchy sequence. And that proves the proposition. And then finally, the second question here, 5.2.2, says let epsilon greater than 0 show that if AN and BN are eventually epsilon close, then AN is bounded if and only if BN is bounded. So let's do that down here. And again, there's symmetry here. So without loss of generality, assume that AN is bounded and that AN and BN are eventually epsilon close for some epsilon greater than 0. Then the members of the sequence of ANs is bounded above, the absolute value of them is bounded above by M for some m greater than or equal to 0 for all n in the natural numbers minus 0, and the distance between AN and BN is less than or equal to epsilon for all n greater than or equal to n for some for all n greater than or equal to capital N for some capital N in a positive natural number. Then the distance between AN minus BN is less than or equal to epsilon, implies that BN minus AN is greater than or equal to negative epsilon and less than or equal to epsilon, which implies that AN minus epsilon is minus m minus epsilon is less than or equal to AN minus epsilon, less than or equal to BN, less than or equal to AN plus epsilon, less than or equal to m plus epsilon. That just follows from the order, the way that we define the order on and the properties of order on the rational numbers. But that implies that minus m minus epsilon less than or equal to bn less than or equal to m plus epsilon, which implies that the absolute value of bn less than or equal to m plus epsilon, which implies that bn is a bounded sequence, and that's the proof. So, and that's it. There's only 2 questions to that exercise set. So like I said, this video is going to be kind of short. So I mentioned this, I think, at the end of the last video, but I got some good things coming up. Not for the channel, just my wife and I are going to do some summary things. So that's going to take up a bit of time for the weekend, and we will continue with this next week. So maybe on Monday, I should be able to post the video for section 5. My summary for 5.3. That section's a little bit long, so it'll take me some time to work through it. And then the exercise set for that is like a medium length solution exercise set. So, but we'll continue this on Monday. So I'll see you guys then. Until that time, keep learning, everybody, and I'll see you in the next video.